Good day everyone, my name is Herman Dorland. I am the Managing Director of Virtual Geomet. Virtual Geomet is a company focused on understanding ore deposits so that 1. The most value is extracted from ore deposit, 2. Plants that perform as expected are built, and 3. The correct value is estimated when resources are evaluated. Today I want to demonstrate Virtual Geomet's software capability to map 2D slices from X-ray computed tomography models for iron ore and simulate seam float from these maps. On the left is a photo of the low-grade iron ore that was used in this exercise, and on the right is a 2D computed tomography model slice through the sample. These images were sourced from the Stellenbosch University CT homepage. This slide shows how the Virtual Geomet software looks. The following functions are present in the software at the moment. Selection of image, assumptions about components, in the case of iron ore the density and the weight percent of iron in the different minerals, specifications about performing the classification from the image, scaling factor in millimeter per pixel, density classes for this zinc float analysis, particle size distribution on which the simulations are performed, and a number of Monte Carlo simulation repetitions. This image illustrates the classification capabilities of the software. On the left is a part of the CT 2D model slice that was shown in a previous slide. The grayscale in the image represents different densities, with low density material having darker gray and high density material having a white color. With this grayscale, 3 components was identified, namely chert, iron alumina, silicates, and hematite. It is possible to include density standards, for example pieces of hematite and chert, of known density in the scans, and then mineral identification can be performed automatically based on density. However, in this example, areas of different components were selected manually by the user, and the classifier then based the classification on this input. 2 iterations of classification, as indicated by the images in the center and right hand side of the slide, were performed to show the repeatability of the classification. Using density calibrated scans will reduce subjectivity significantly for this type of exercise. The assumptions used for the minerals are shown in the table, with density calibration. Assumptions about iron, alumina, silicates will improve. 2 sets of zinc float simulations were performed. The particle size distribution of the first set of simulations that use larger virtual particles are shown in the table. The set of zinc float simulations for the larger particles are shown in the table. Iron content and yield are cumulative. The cumulative zinc float yield versus density and iron content versus density are shown. There is some variability between the curves. For example, if a product iron content of approximately 60% is required, the yield can vary between 45 and 55% at a zinc density of 3.5 grams per cubic centimeter. The software can include any wanted density ranges. The densities in this set of simulations were chosen to make display of the graphs easy. A second set of simulations were performed on the same sample using smaller virtual particles in the particle size distribution. The particle size distribution used is shown in the graph. A cumulative zinc float table is shown in this slide. Note that the total iron content is about 48% compared to the 50% of the classification for the large particles. This is a percentage point variability of 4% between the 2 classifications. There are less variability between simulations for the smaller particles compared to the bigger ones. If a product iron content of 68% is required, yields is between 54 and 57%. Comparing the yields for different products, the benefits of crushing to finer sizes can be analyzed and compared to the disadvantages associated with smaller particles. The following conclusions can be made from this experiment. Density mapping and mineral identification is possible using CT. Using a density calibration method, mineral identification and density of components can be automated. Zinc float simulations for different particle size distributions can be obtained for samples. This will enable resource estimations that are based on specific particle size distribution. Value propositions can be analyzed using smaller or larger particles to demonstrate change in resource value with change in particle size. This will lead to more accurate value determinations, especially of lower grade iron ores. The zinc float characteristics of the iron ore is determined in much more detail than a single float test per sample. Again, the zinc float characteristics is understood in greater detail, leading to improved plant designs and plants that produce as predicted. Thank you for listening.